Good morning, ladies and gentlemen. I hope that everyone is well and that you had a fantastic weekend. Today, we're continuing our exploration of work, yes, but we are in a unit where we are going to explore energy. And as I stated on Friday, the first thing we had to do was define the term work. In the physics realm, the term work, because the definition of energy itself was or is the ability to do work. So on Friday, we defined what work actually is and learned how to determine when work is done or not. So I want to take you to an image and revisit that before I introduce you to today's concept. All right, so work itself, the first thing we had to do was determine whether work was done or not, which required an understanding of the application of the definition. So work is force times distance. That's that is true. However, we have to know when force applied over a distance is actually considered work and when it is not considered work. So I really like this diagram because it reiterates the point and gives us a visual of what's happening. Like I'm pointing at it with my pencil, as if you can see that, sorry. All right, so for work to be done, we have to have a force that's applied over a given distance. So a force that causes or creates motion. The caveat is that the force has to be applied in the same direction that the object is moving. So in this instance, the person is pushing the box. The force they're applying is in this direction. The motion of the box is also in the same direction. The opposite of that is the young lady is carrying a bag. So she is applying a force to the bag, otherwise the bag would fall to the ground. But the force that she's applying to the bag is in this direction, it is up. So it is perpendicular to the motion or the direction that the bag is actually moving when she's walking with it. Okay, so we had to determine whether work was being done or not. All right. And then on Friday, you learned how to calculate work. So let me get out of this and jump back over here. All right. So we found or learned that work happens when we have a force that is applied over a distance. Work we learned was in units of joules. That's a new unit for us. And energy is also going to be in that same unit. We learned in our previous unit, when we were studying forces in motion, that the unit of force, the unit of force is a Newton. And then distance is going to be measured in units of meters. Okay. All right. So we learned how to use this equation on Friday. All right. So today we are exploring a new concept that is related. And again, the definition that will apply is a little different than what we tend to think in everyday life, right? So when you think of work generally, we think of some place that we go in order to earn money, like I'm at work right now. But we redefine that in terms of some measurements, the physical definition, force times distance. So today we're going to explore the concept of power. And if I could have figured it out, I was going to play an old school song, which you probably have heard. Anyway, power. So by definition, power is when work is done in a given amount of time. Another way to think about this is actually how quickly work is done. So mathematically, the definition is work over time. So how much work can be done in a given amount of time? So now in the physics realm, when we're defining power, we're talking about how quickly work can be done. So here's a classic example, right? If I draw a set of stairs and I have a person who is going to go up those stairs. Thank you for bearing with my poor illustrations. Okay. So they have to apply a force to themselves in order to go up the steps, right? So they're applying a force in this direction, okay, in order to get themselves up. Okay, so and the direction of their motion is also up. So work is indeed being done. All right, so power is about how quickly work is done. You can try this at home or challenge your little brother or sister. Please don't hurt yourself. So if the same number of steps, so let's say this is a distance of 1 meter, okay, that is being traveled. And if we were in class together, we would go out in the bleachers, out in the stadium, and take some measurements and time ourselves, actually. You want to walk up the steps. So let's say when someone walks up the steps, it takes them let's say 10 seconds. When they run up the steps, it only takes 5 seconds. Okay. Our physics definition of power is which one did work more quickly, right? So let's say the weight of the person, and recall there's a difference between weight and mass, and we looked at that last week or the week before. Mass is in units of grams because it's a measure of how much matter is in an object. Weight is a force because it is a measure of the acceleration due to gravity on mass. So we could calculate weight like this. So the unit, not force, I'm sorry, the unit of weight is a Newton. Okay. So I'm revisiting that because we're going to say that this person has a weight of 50 newtons. So if they have a weight of 50 newtons and they're traveling a distance of 1 meter, then the work that they do is carrying that 50 newtons over 1 meter. So they did 50 joules worth of work. So let me say that again. The weight of the person, and weight is equivalent to a force, okay, because recall the difference between weight and mass. So we ascribed a measure of 50 newtons, so the person has a weight of 50 newtons. So they're going to apply a force. Then we can assume that in order to move that 50 newtons, they have to apply a force of at least 50 newtons to take themselves up the steps. Okay. So the force in this direction is 50 newtons. The distance that's being traveled is 1 meter. So we calculated how much work was done for this person to get to the top of the steps. Now, power is about how fast that work was done. So if you walk up the steps, if power is equal to work over time, 50 joules, you walked up the steps in 10 seconds, then you did 5 watts of power, or you had 5 watts of power. So this is new. We are familiar with work, we're familiar with time. I just defined power, but this is new. So the unit of work is called a watt or watts. So you see this on electronics at your home, kilowatts, right? It's how your electric bill is measured in kilowatts. We'll talk a little more about that in the coming days. Okay. So let's call this person Jane. When Jane walked to the top of the steps and took 10 seconds, then her power was 5 watts. She exerted 5 watts of power. Versus if Jane runs up the steps, she's still done 50 joules worth of work, but she did it in 5 seconds. So her power is 10 watts. So then what we can deduce, even from this example, is power is about time relative to work, and the faster you do something, the more power you have. The faster you do something, or the less time, the more power. These are inverse. Okay. All right. So we know power. We know what power is, work in a given amount of time or work over time. We know the unit of power is now the watt. And I want to just point out one other thing before I walk you through how to execute some calculations here. Notice that our work was in joules per second, okay? And we called it a watt. So a watt is specifically joules per second. So your time unit has to be in seconds. Now, I'm not going to ask you to do any additional conversions to get there. The example that one of the examples that I'm about to do for you is going to require me to do that, but I'm not going to ask you to do it on the practice problems that I'm assigning for you. Okay, so let me walk you through using the calculation. Before I do that, let me remind you of our little tool to help us navigate the algebra when we're dealing with a 3 or 4 variable equation. Okay. So I introduced you to the triangle several times, but I'll revisit. If a number is on top, then whatever's beneath it will be divided. Okay, divide this by that. If they're beside each other, then we're going to multiply. So if we know that's the relationship of the numbers, when we look at the equation for power, what we know is that work is divided by time. That's how I know how to put it in the equation, and then fill in the power is equal to that. Let me just revisit work because I'm gonna do the first couple of examples I have are gonna require that we do work as well. So divided, multiplying when they're beside each other, and we know that work is force times distance. So how do I know how to put my equation in the triangle? Force is multiplied by distance. When they're beside each other, they're multiplied. That's how I know to put force times distance on the bottom, and then just fill in for work. All right, so a few examples, and I'm going to draw these triangles up here. Work is equal to force times distance. Power is equal to work over time. All right, so the way that I want you to approach all problems is to list the variables first. And I know it's a little tedious and cumbersome, but I promise that it pays dividends in the end. Because again, right now, you know that this is going to be a power problem because I'm telling you it's going to be a power problem. But on your test, you have to discern based on the information given in the question what type of problem it is and what you need to get there or to solve it. Okay, so let's list the variables that are given. A set of pulleys is used to lift a piano weighing 1,000 newtons. So it weighs 1,000 newtons. Newtons, even if you didn't recall that weight is a force, newtons tells me that that's a force. The piano is lifted 3 meters. Lifted 3 meters. Meters is a distance measurement. So distance is 3 meters. In 60 seconds, seconds is a time unit. So we know we were given force, distance, and time. We're asked to solve for power. So we know that power is equal to work over time. And the problems that I'm asking you to do today won't combine these in the method that we're about to use, but I'm going to ask you to do both work and power problems today, so it serves us to see them both in action, okay? So power is equal to work divided by time. Do we have work as is? No, we don't, but we do have force and distance. So work is equal to force times distance, which means we can calculate work. Again, in the practice problems I'm going to ask you to do today, you're not going to have to do both steps of this, but I decided to use this example just to revisit how to find work, because you will have to do that today. All right, here we go. 1,000 newtons, 3 meters. So work is equal to 3,000, and what is the unit of work? Joules. But we're trying to solve for power. That was the ultimate question. How much power? So power is equal to work over time. Now I have work. Do I know time? Yes, it was given in the problem. Work divided by time will give me my solution. What did we say the unit of power is? Watts. And in fact, you may want to, as you're using the triangle, especially as you start, write the units beside them, beside it on the triangle, so it'll help you remember what's going on. So work is in joules, time is in seconds, power is in watts. Work is in joules, distance is in meters for work, and force is newtons. All right, so when I plugged all this in, I got 50 watts because watts is the power, the unit of power. Let's do one more like this and then jump down where it's exclusively power. How much power, so that's what we're looking for, is used if a force of 35 newtons, and they tell me it's force in this problem, but even if they didn't, I would know because of the unit. It's used to push a box a distance of 10 meters. So they told me that it was distance, but I could also recognize it by the unit in 5 seconds, which gives me my time. Like the previous problem, we need to find work first because work was not given in the problem. So work is equal to force times distance, 35 newtons times 10 meters. It's 350 joules. Okay. Power, however, is equal to work over time. This is our work. We just calculated it. And again, I'm not going to ask you to put these two pieces together. I just chose to do these examples so that I could revisit work while I was introducing power. Okay. So time is 5 seconds. And when we plug that in, we get 70 watts. I'm going to jump down and do a problem where we're going to manipulate the power equation. So we want to know how much work is done. So we're looking for work using 500 watt, using a 500 watt microwave. So watts is a unit of power. So they gave me power. And the oven, it was in the oven for 5 minutes. Okay. So again, today I'm not going to ask you to do a time conversion. So I'm going to just go ahead and give you what this is. 5 minutes is actually 300 seconds. And we have to be in seconds because that is the time unit that makes power watts relationship. All right, so we want to know work. Well, if we use our triangle, it makes the algebra simple, super simple. Okay? If I'm solving for work, what does it tell me to do with power and time? They're beside each other, so it tells me I'm going to multiply them. So work is equal to power times time. Now note the difference. Okay, so it asks you to solve for work, but it's not a straight up work problem, which is why you needed to list the variables and pay attention to the units. Okay. All right, so now we're home free, right? Multiplying 500 watts times 300 seconds is going to give us joules. So for this, it's a big number, 150,000 joules. And we're in joules because we were solving for work. All right. I want to show you a couple of the worksheets that I'm giving you today, and then I'm going to call it good. So a part of today's assignment, it's entitled Energy, Work, and Power, but this front sheet is just information. There's nothing for you to do on page 1 of today's assignment. These are actually notes. Okay, so it tells you about energy, it tells you about work, and some specifics about work, right? If you push an object harder, you do more work. If you push an object longer, you do more work, right? So these are notes about work and about power. So at the bottom of the page, it introduces you to power and gives you a couple of power examples. On the back of the sheet, we're going to answer some questions. So in this first block, what you're doing is matching the unit with the appropriate measurement. So for instance, F is force. What unit represents force? Newtons. So that would be 30 newtons. Okay. So all you're doing is matching the unit with the force. You don't know mechanical advantage, and you won't know that for a few days. It doesn't have a unit, so I'll go ahead and give that to you. Okay. Number 2, W or E is meaning work or energy. Let me zoom in a little bit. Okay. Work or energy. I'll give you this one because we didn't study momentum, kilogram meters per second. Power, distance, work, energy. Okay. You're just matching the unit with the measurement. In this matching, you're matching definitions. Okay. What's a joule? What's work? Okay. In this block, you're going to indicate whether more work is done, less work is done, or the same amount of work. So you use more force to move an object. If you use more force to move an object, did you do more work, less work, or the same amount of work? And you can refer to the front of this page to help you with that concept. Again, here, you're simply answering, is the person doing work at all based on the scenario? In this block, you're looking at whether they did more or less power. So an engine can lift an object faster. Well, what do we know about power? That how quickly you do something increases the power. So the more quickly you do it, the more power you have. And then below are some problems, okay? So you're solving for work. Here you're solving for distance using the work equation. I'm not going to give that all away to you. So read the questions and I want you to show me your work. List the variables, show me the setup of your work. Okay? So these are some problems, but I'm giving you some additional problems because in my experience, I know the value of practice and drill. So if we were in class together, you would do a set of problems as classwork, and then you would have a set of problems to do as homework. So we're just kind of doubling up because this is your class time, right? So you're going to do numbers 1 through 9. Again, I want you to list your variables, show me your problem setup. What equation did you use and how did you use it? Where did you plug in the numbers? So just like I did in my examples, I listed my variables. I showed what equation I was using, and then I plugged in my numbers. Okay, that's how I want you to do it. Please let me know if you have any questions. I'm going to post this, but I'll have office hours today from 1:30 to 2:30. Hope everybody has a great day. Bye.